Okay, so what we're going to talk about now is another way of measuring angles, and this is called angle measure in radians. And if you remember, it was at the beginning of the semester in the first few lectures we talked about ways we could identify angles, and one of them was in radian measure, and I said, hey, we'll talk about them later. Well, this is when we're going to be talking about them. And of course, radian measure have their advantages, like for instance in calculus, everything applies, all the trig functions that you deal with in calculus apply for radian measures only. So you could already see how important radian measures are. So, and that's kind of like a conversion where we'll be converting and so on. So let's go ahead and define what a radian measure is. So radian measure of an angle. So let's first go ahead and define what this is. So we would say if theta is a central angle of a circle with radius r and is subtended by an arc length S, then the measure of theta in radians is defined as theta is equal to S over R. Okay, so visually speaking, what we're basically saying is if let's say we have, so here's what this is saying, if we have, let's say, a circle, and I'm going to center it at the origin kind of just to show you guys how this central angle we talk about, we can translate it and talk about it as an angle in standard position. But a central angle obviously for a circle occurs where? At the center of the circle. So if I draw this angle out, so that's theta, and then this is R, right? And then we have this right here is my arc length. So what basically saying is theta, one way of looking at it is we know that in previous courses you may have also seen that the way you find arc length so the arc length depends on the radius and theta. So the larger the radius or the larger the theta, obviously S becomes larger. So if this is how we find the arc length of a circle, then this shows that theta is equal to S over R, and we can go back and forth. But based off of this picture, that's kind of what we're looking at. So this angle theta could be described in radians by taking the length of the arc length and dividing it by the radius, which would then give us what theta is. So let's start off with our first example where we'll put this to use. We'd say that if a circle has a radius of 2 centimeters and an arc length of S, which is 12 centimeters, what is the radian measure of theta? Okay, so with that said, what we have is, if we were to kind of draw a picture of this, here's what we're saying is, look, we have a circle that's has radius of 2, and then we have kind of like and we're told that this arc length is about 12, which would put us somewhere around here. So we're trying to figure out what that theta is, right? So with that said, to find basically the radian measure theta, we know by definition theta is equal to S over R. So it's not like you needed that picture. I kind of want to show you that picture, but then this becomes, we know that it's 12 over 2, which is 6 radian, right? And then so remember, just so whenever you're writing an angle in radian measure, make sure to write the word radian. So if it's like 6 degrees, we would put the 6 degrees there. So we're trying to be specific, okay? So what we're going to do now is, since we're describing angles in radians, we should obviously have a conversion between radians to degrees and vice versa, from degrees to radians. So our goal is now to convert angles from degrees to radians, and as well as radians to degrees. And to do this, we're going to need our conversion factor, right? Like, for example, how many radians is there in a degree, or vice versa. So, and I'll give that to you. So we're going to say, to do so, we need the conversion factor, which is pi radians is equal to 180 degrees. Okay, so, and by the way, this can be easily shown by using the fact that, hey, 2 pi is a complete circle, so pi is half of a circle, and half of a circle takes on a central angle of 180 degrees. So we can see why this conversion is the way it is, because we know that if you go around the entire circumference of a circle of radius 1 is going to be 2 pi, so half of it will be pi, and if half of it is pi, that makes a straight angle at the center, so it's 180 degrees. So that's the conversion rate that we need, or the conversion factor. So now we can then say, so let me go on to the next page. So the conversions should not be difficult. So then we could say, look, thus, to convert an angle from degrees to radians, we will do the following. So what will happen is, obviously, if I'm converting from degrees to radians, my angle will be in degrees, will be given. So I want to convert this. I'm going to use my conversion factor. And what was my conversion? For every pi radians, it's 180 degrees. Now, if I want to cancel the degrees and go to radians, then I need to make sure that the 180 degrees is in the denominator and the pi radians is in the numerator. And if you complete this process, you would have converted your angles from degrees to radians. Okay, and then we could also say converting from radians to degrees. At this point, I'm pretty sure you know how that's going to work. We're going to go backwards, right? So what will happen is we'll have our angle in radians, and then we're going to multiply that by 180 degrees over pi radians. So this way now the radians are going to cancel out and I'll have my angle in degrees. So with that said, let's put up example 2, and you might want to pause the video and then you guys do this on your own and then play and then, you know, compare your answers. So we're going to say convert each angle from degrees to radians, and then we're going to say write each answer in exact form. So which means if we say write each answer in exact form, that means I want to leave my answer in terms of pi. Okay, so if it's set write it in approximate form, then you'd use your calculator and approximate it or round it to the nearest whatever they want you to round to. So if I have A is negative 75 degrees, B is 250 degrees and 12 minutes, C is 135 degrees. Okay, so let's look at A first. So if we're looking at A, I'm going to take negative 75 degrees and I want to convert this to radians, which means I would have to multiply this by pi radians over 180 degrees. And then what would this simplify to? I know that they both divide by 5, so let's simplify a little bit. This would be what? So the degrees will cancel out. So I'm dividing both of these by 5, so negative 15 pi over 180 divided by 5 would also give us 36. And it looks like I could simplify this further because they both divide by 3, so that would be negative 5 pi over 12. And that I can't simplify any further, so that's my answer. Okay, now the 250 degrees in 12 minutes, what I would do is let me first write this in decimal degrees, right? So in fact, on your most recent exam, you were asked to do something like this. So let's write this in degrees, minutes, seconds. So the 250 degrees we're good with. The 12 minutes I want to convert to degrees, which would mean I would have to multiply by, we know that 1 degree is 60 minutes, and then 12 divided by 60 is going to give us 0.2 degrees. So then this becomes 250.2 degrees. Now to convert this to radians, I would have to just multiply by pi over 180. Okay, and then if I do that, I get 250.2 over 180 pi. And see, for maybe something like this, it would have been better if we approximated it, just because I have a decimal. So if I were to grab 250.2 and divide it by 180, and then multiply that by pi, all right, so this is just literally calculator usage. If I multiply that by pi, then I get roughly, and if I round it to the nearest tenth, it would be about 4.4. Okay, but for the nice numbers where we don't have decimals, we probably don't want to do that. We want to leave our answers in terms of pi. So 135 degrees multiplied by pi over 180. Now you're starting to see a repetitive or a common theme here. So this one, I believe they both have a 45 in common, so this would become 3 pi over 4. So that's what it simplifies to. Okay, so the next example is going the other way. So for example 3, we're going to say convert each angle from radian to degrees. And for this one, we could say write each result in exact form and approximate form. Okay, so for A, pi over 24, I want to convert this from radians to degrees. So I'm going to multiply pi over 20 by what? 180 degrees over pi, which then these the pi's cancel out and I get 180 over 24. And 180 over 24, I know that they have, let's see, this becomes 45. I know they both divide by 4. This becomes 45 over 6. And they both divide by 3 as well, because that becomes 9 over 3. Is that right? I think I may have made a mistake. 180 divided by 4 is 45, 24 divided by 4 is 6. That's correct. The problem was 15, not 9. 15 over 3. Okay, so that's what it is. And then if I want to put it in approximate form, I mean, this would just mean it becomes, it's not approximate actually, it becomes 7.5, doesn't it? Because 15 divided by 3, or no, 15 divided by 15 divided by, this should be a 2. I can't divide. So there you have it, 15 over 2, which is 7.5. That's not approximate, that's actually exact. But if it was like, let's say, a non-terminating decimal, then I would approximate it. Okay, so for part B, same idea, it's just -5. So the way we would convert this to, this is -5 degrees. Now to convert this to radians, I'll just multiply by pi over 180. Sorry, the other way around. This is radians, not degrees. We're going the other way. So it'll be 180 over pi. So then this becomes -5 times 180 becomes 900 over pi. And then if I want to approximate this, then this becomes about, if I divide by pi, I get about -286.6. Okay, so there's our approximation. Okay, so the last thing I want to talk about, this is kind of like a review. So, but it's kind of like a nice result that we get because of some of the problems we're working on from last section, which you probably may have noticed, or hopefully. So my question is, do you see a pattern of exact values of trig functions of angles that have the same reference angles? So what am I saying? So because if you remember, reference angles were important in the previous chapter when we were working with larger angles. So for instance, my question to you is, what do you notice about the exact values of 45 degrees, 135 degrees, 225 degrees, and 315 degrees? So do we see a kind of a pattern here? And I'll show you in a minute, but these angles that I've picked, even though they're different angles, they all have the same reference angle. So we're going to see the importance of a reference angle. The answer to this question is yes, there is a pattern. So which anytime we see a pattern, that's good news because you have a good idea as to what the answer to your exact values are going to be. So if they have the same reference angle, then the same trig functions with angles that have the same reference angle will have the same numerical value. Which I think that's crucial, because if you know that they have the same reference angle, numerically they'll have the same value. There will only be one difference. The only difference is they only differ in signs. where one might be positive, the other one might be negative, but that's not an issue because if we know which quadrant we land in, then we'll have a good idea. So which depends on the quadrant they land in. So let me show you the example for 45, 135, 225, 315. Reason why I'm saying this is your work could be minimized. See, if let's say we are talking about 45 degrees, right? So let's talk about 45 degrees first. If we were to draw the angle out, pick a point. This is a 45, 45, 90 triangle, and it's 1, 1, rad 2. And then what is it that we notice for 135 degrees? For 135 degrees, if I draw it out in standard position, what's my reference angle? It's 45 degrees again. If I draw my angle or my triangle, I get -1, 1, rad 2. What do you notice about these values? They're the same, except one of them is negative. So for instance, like tangent of 45, which is y over x, I get 1. Tangent of 135, which is y over x, I get -1. Notice how they both have the same numerical value, except in quadrant 2, tangent's negative, but in quadrant 1, tangent is positive. So what do you guess, for instance, tangent of 225 would be? The numerical value, it'll be 1. Now, whether it's 1 or -1, we'll see in a minute, but this is what -1, -1 rad 2, right? And once again, I get a 45, 45, 90, and tangent of 225 is -1. Or no, sorry, not -1. Y over x is +1. And then lastly, tangent of, let's say, 315 degrees, which puts me down here, that has a reference angle of 45 as well. And what do you notice about the x, y, and r? 1, -1, rad 2. So tangent of 315 is -1 because it's y over x. So what is it that you notice? Are we surprised that tangent of 45, 135, 225, and 315 all had a value of a 1, ignoring the signs, the value? They're all 1s? No, because they have the same reference angle. So the good news is if you know the trig functions of 30 degrees, 45 degrees, and 60 degrees, then you know the trig functions of all the other larger ones that have the reference angles of 30, 45, 60. Numerically, they'll be the same. You just need to figure out which quadrant they land in. And I just want to share this with you because it just, for me at least, it simplifies things. It makes things so much quicker and cleaner. So, for example, if I know what the cosine of 30 degrees is, then I know what the cosine of 150 degrees is because they both have the same reference angle. So I don't need to waste my time doing more work that's unnecessary work. Okay, so this takes care of this section. As always, feel free to email me if you have any questions about any part of the notes.